We have so far discussed electric circuits containing capacitors in series and parallel, electric circuits containing resistors in series and parallel, and we saw Kirchhoff's laws for loop circuits. Well, let's combine all that together in one type of a circuit. We will now discuss RC circuits, resistor capacitor circuits. A circuit that contains a resistor and a capacitor is called an RC circuit. Now here I have the diagram of a simple RC circuit. You have a capacitor that has a positive pole and a negative pole. The negative end of the capacitor is connected to the negative pole of the cell, and the positive pole through a cell through a resistor to the positive of the capacitor. Now the circuit shows a resistor R and a capacitor C connected in series. Is that right? This is a series connection across the poles of a cell of EMF E through a switch. Now when the switch is closed, what will happen? Electric charges will flow through the resistor onto the capacitor plate, establishing a current in the circuit. Now tell me, what do you think will happen to the current with time? Will the current remain steady? Well, what happens is, as electric charges continue to flow from the cell to the capacitor plate, the current will start decreasing. You know why? Because initially the rate of flow of charges will be quite high. The current will be very high. As the capacitor gets accumulated with more and more charge, the rate of flow of charge will decrease. That means the amount of charge on the capacitor plate will increase gradually to a maximum, and the current in the circuit, the current flowing through the resistor, will decrease steadily. That is what we would expect. Is that right? Does it make sense? Because the role of the capacitor in that circuit is, when you connect the cell to a capacitor, the capacitor gets charged. And when the capacitor is fully charged, there will be no more flow of charges in that circuit. That means the current initially will be very large because there are no charges on the capacitor plates. Now, as the capacitor plates accumulates more and more charges, the rate of flow of charge will decrease. So when the switch is closed, electric charges will flow from the cell to the capacitor plate, establishing a current in the circuit. The capacitor plate connected to the positive pole gets positively charged, and of course the other will then get negatively charged. Initially, when the capacitor plates have no charge on them, the rate of flow of charges will be large and the current is maximum, and the current then will be given by this. This is the maximum current. I0 equal to E over R. That means the capacitor, there are no charges on the capacitor at T equal to 0. The current then will be E, the EMF, divided by R. This is the maximum current. Ohm's law equation. I equal to V over R. V is the EMF of the cell. So the current now will be, maximum current will be E over R. As the charges get accumulated on the capacitor plates, the flow rate decreases, and so the current will decrease. Alright. When the capacitor is fully charged, there will be no more flow of charges in the circuit, and hence the current will reduce to 0. As the amount of charge on the capacitor plates increases, the current in the circuit decreases. So if you can visualize a graphical representation, the amount of charge will keep on increasing, reaches a maximum, right, sort of asymptotically. And the current will be a maximum in the beginning given by E over R, and it will continue to decrease to 0 after a very long time. Alright, if VR is the potential drop across the resistor and VC is the potential drop across the capacitor, we can apply Kirchhoff's laws, Kirchhoff's second law, in the closed loop circuit. Alright, do you remember Kirchhoff's second law? What does it say? It says in a closed loop circuit, the algebraic sum of the potential drop equal to 0. That means if you add the potential drop across the resistor to the potential drop across the capacitor to the potential drop across the cell, which is the EMF, that sum will be equal to 0. That is what Kirchhoff's law says. So now we're going to apply Kirchhoff's laws in a capacitor-resistor circuit. Can you help me do that? If E is the potential drop across the cell, VR is the potential drop across the resistor, and VC is the potential drop across the capacitor, then E minus VR minus VC will be equal to 0. This is what we call the algebraic sum of the potential drop will be equal to 0. At any given time, if Q is the charge on the capacitor, then the potential drop across the capacitor will be Q over C. Now this is an equation that you're familiar with from the definition of capacitance. The capacitance is Q over V, therefore V equal to Q over C. So the potential drop across the capacitor is Q over C. How about the potential drop across the resistor? Now, those who have done an elementary differential equation would know how to solve this. I'm not going to do that for you here. I'm going to give you the solution. Now, the solution of this differential equation, solution will be for what? The dependent variable here is Q, and therefore the solution will be for Q. Q will be given as a function of time. So the solution of this differential equation will give you Q, the quantity of charge, as a function of time. Now this is the solution of that differential equation. Q equal to CE times 1 minus e to the power negative t over RC, where C is the capacitance, E is the EMF of the cell, R is the resistance, and so on. Now what does C times E represent? If you charge a capacitor with a certain amount of charge Q, then we can say that Q equal to CV. Here E stands for the EMF, which is the potential difference. So C times E is the maximum amount of charge on the capacitor plates. You see that? That means when this time is very large, can you tell me what will be the value of this quantity when this T is very large? Now let me ask you this. I'm sure some of you have experience with this. What is the value of limits T approaches infinity e to the power of negative t? What is the limiting value of e to the power of negative t? Well, you know e to the power of negative t is 1 over e to the power of t. And when t becomes infinite, the denominator becomes very large. So this quantity is 0. limit t goes to 0, e to the power of negative t is 0. So if you look at this equation, it gives you exactly what happens to the quantity of charge. When t equal to 0, what is the value of, when t equal to 0, what is the value of q? Let me see if your mathematics, your understanding of algebra will let you do this. What is the value of this quantity when t equal to 0? Well, e to the power of 0 is 1. 1 minus 1 is 0. That means at t equal to 0, when you set up this connection and start the clock, at t equal to 0, the amount of charge on the capacitor plate is 0. And as time increases, the amount of charge will increase. Now, and as time increases and as time goes to infinity, after a very long time, the amount of charge will, this quantity will be then 0, and the amount of charge then will be equal to CE, which is the maximum amount of charge. Alright? I hope you're following what I'm saying. In the beginning, when t equal to 0, the value of this is 1. That means q when t equal to 0 is 0. And when t equal to infinity, it means after a very long time, this quantity will be 0. That will be q then will be equal to CE. And CE is the maximum amount of charge on the capacitor. So as time increases, the amount of charge will increase. After a long time, it will reach the maximum value. Alright. Since E is the maximum voltage, E is the maximum voltage, the EMF, across the capacitor, CE equal to QF. In other words, that is the maximum charge on the capacitor. I can replace the CE by QF. Why did I use F there for QF? QF is the amount of charge at the end of the charging cycle, the final. So CE equal to QF. Therefore, the solution of this equation is Q equal to QF times 1 minus e to the power negative t over RC. Well, that is the equation for charge as the capacitor gets charged. Now, I'm going to do a little manipulation here. I'm going to say let RC equal to tau. Now, we actually discussed this in connection with Newton's law of cooling, a very similar situation. When RC equal to tau, this equation can be written as Q equal to QF times 1 minus e to the power negative t over tau. And this tau has a significance for this circuit. Tau is called the time constant of the RC circuit. Alright, I thought I have written down there, but I think maybe I'll have it later. What is it? What is tau called? Tau is called the time constant of the RC circuit. Well, what is tau equal to? Tau equal to RC. That means the time constant can be adjusted by varying the values of R and C. Now, we can write a similar equation for voltage. You know that as the amount of charge on the capacitor plates increases, the voltage across the capacitor plates also increases. So, if Q equal to QF times 1 minus e to the power negative t over tau, that means voltage V equal to VF times 1 minus e to the power negative t over tau. This is how the voltage will change. So, what is the variation of voltage like? The voltage across the capacitor will be 0 in the beginning, and as you turn the switch on, the voltage will increase and reach a maximum gradually. where tau equal to RC, the time constant. Now here, Vf equal to E, the EMF of the cell, and tau equal to RC is called the time constant of the RC circuit. Every RC circuit has a time constant, and that time constant is the resistance multiplied by the capacitance. The charge and the voltage on the capacitor grows with time, reaching a maximum value asymptotically. I'm sure you understand the meaning of asymptotical approach. Now, it takes a very long time to reach that maximum value. Now, this is how the amount of charge is 0 in the beginning, and with time it will increase and it will approach asymptotically the QF equal to CE. That is the horizontal asymptote. It will take a very long time to reach that value, and tau equal to RC. The charging current is maximum in the beginning. Why is the charging current maximum in the beginning? Because the rate of flow of charge from the cell to the capacitor plate will be a maximum in the beginning. And as the capacitor plates accumulates more and more charge, that rate of flow will decrease. And what is the maximum current equal to? Well, the maximum current in this resistor will be I0 equal to E over R. We use the Ohm's law equation, I equal to V over R. V in this case equal to the EMF of the cell. So the current in the resistor will be RC by tau. So that becomes I0 e to the power negative t over tau. Now tell me, looking at this equation, what is the value of I when t equal to 0? When t equal to 0, the value of this quantity e to the power of 0 will be 1. Therefore, the value of I when t equal to 0 is I0. Alright, what is the value of I when t is very large, after a very long time? What is the limit of this quantity when t goes to infinity? Will be 0. Therefore, the value of I after a very long time will be 0. We say the current decays. The current decreases from I0 to 0 after a very long time. So, in a resistor capacitor circuit, as the capacitor keep on charging, the charge and the voltage increases with time, and the current will decrease with time. Well, so as the charging continues, the current decays exponentially to 0. Now this is how the current will decrease. The current in the beginning is I0 equal to E over R, and as time goes on, the current will decrease, and tau equal to RC is the time constant. Well, let me see if I can show that to you. Let me set up an RC circuit for you. Alright? I'm going to use a ready-made RC circuit. Now, this is a ready-made RC circuit. If you look at this, actually I showed this to you in an earlier lesson. Now, here is the capacitor and here is the resistor. This is a resistor. And you can see the value of the resistance is given as a color code. Now, if anybody is interested in knowing how to read the color coding on a resistor, let me know. I will get back with you. So, this is a resistor. This is the capacitor. And I'm going to connect a power supply across these 2 points. I'm not going to use this cell. That means I will be driving a current through the resistor. Alright, through the resistor, I will connect B to A so that then the current will go through the capacitor. You see, the current will pass through the resistor. Through here I will bridge these two, and then it goes through the capacitor and back. That will be the RC circuit. Alright, now let's set it up over here. Now I hope you can see this. Well, this is my RC circuit. It doesn't sit there, so I need to get something to prop it up. Let me see if I can do that. Well, that is the RC circuit. And I have connected the power supply, the battery, across these two terminals. And what I'm going to do is I'm going to connect a voltmeter. Now here is the voltmeter which you have seen before. Alright, that is the voltmeter. I'm going to connect it. Let me first of all connect it, because these wires are not very friendly, so I need to be a little creative to do these connections. And I also need my glasses to see this. And in the meantime, I have dropped these pieces of wood which was propping up the capacitor circuits because of the stiffness of these wires, you see. Okay, let me see where I need to connect that. I'm going to connect the capacitor, the positive there, and the negative here. So I have now connected the capacitor. Now here are the connections for the cell, and so the current will now come through the resistor. Can you see that? The current will come through this resistor, and I have now connected between these. It will pass through here, go through the capacitor and back to the cell. And since I don't have a meter that will measure the amount of charge, I need only measure the potential difference. When the charge on the capacitor plates increases, the potential difference will increase. So I'm going to use a voltmeter to measure the potential difference across the capacitor. And here is the voltmeter that will measure it. Alright, now let me see. If I turn the switch on to charge and turn on the voltmeter, now I want you to watch how the reading of the voltmeter change. I'm going to turn on to charge and see how the voltmeter reading changes. You can see the voltage across the capacitor plate is increasing. Is that right? The voltage is steadily increasing. That means the amount of charge going into the capacitor plates is becoming, the amount of charge on the capacitor plates is becoming greater and greater and greater. And this is going to take a long time because the battery is a 6-volt battery, and you can see the potential difference is increasing, and it is going to go asymptotically to the maximum voltage. What is the maximum voltage? The maximum voltage is the EMF of the cell, and it will take a very long time to get there. Well, so this is how the voltage increases, and when the voltage increases means the charge is increasing. Now tell me, what happens to the current? The current, as the charging continues, the current is going to decrease. Now that means if I now measure the potential difference across the resistor, what will happen to the potential difference across the resistor? If the current is decreasing, that means the current in the resistor is becoming smaller and smaller. That means the potential difference across the resistor should decrease. As the potential difference across the capacitor increases, the potential difference across the resistor will decrease because the current is decreasing. So, let me see. I'm going to remove this connection from the capacitor. You can see the voltage has now reached 4.5, is reaching gradually 6. It will take some time. Now, I'm going to disconnect it, and what I'm going to do is disconnect from the capacitor and connect it to the resistor, and let's see how the potential drop across the resistor now look. Now, if you watch this, the potential drop across the resistor now is actually in millivolts. It's very, very small. That means the current has become very small. The potential difference is across the resistor is very small. This is not volt, this is millivolt, and it's still decreasing. You see that? The potential difference across the resistor is decreasing, while the potential difference across the capacitor is increasing. So this is what happens when you charge a capacitor. The amount of charge on the capacitor plates increases, thereby increasing the potential difference across the capacitor. And the current in the capacitor decreases. That means the current in the resistor decreases. And that's the reason why the potential difference in the resistor decreases. Voila. Let me see if I can show a similar thing on the computer. Here we have the RC circuit. This is the capacitor, this is the resistor, and we have a 6-volt battery connected all in series. Now, if I turn it on, I want you to watch how the potential difference across the capacitor changes and how the potential difference across the resistor changes. It is animated here and you can watch it. And a graph will be drawn, voltage across the capacitor and current. What would you expect the voltage will behave? Voltage will increase, reach a maximum with time, and the current will start at a maximum value and decay exponentially. The potential drop across the capacitor will increase because the amount of charge increases, the potential drop increases, and the potential drop across the resistor will decrease because the current in the circuit decreases. Alright, watch that as I turn it on. There you are. Potential drop across the capacitor increases, across the resistor decreases, and the charge increases asymptotically, the current decreases. You can see how beautifully depicted in this animation. Alright, watch that one more time and I will turn it off. The charge grows on the capacitor. The potential drop across the capacitor decreases, showing that the current is decaying. So the current in the circuit decays, the voltage grows along with the charge. Okay. If you remember, in the lesson on capacitor, I showed you how a capacitor is charged and then use that charge to light a bulb. So, during the time the capacitor gets charged, the charges flow from the battery to the capacitor, and when you take that charge out, the charges flow out of the capacitor to a resistor. The bulb is a resistor. So what is the meaning of discharging a capacitor? How do you discharge a capacitor? Discharging a capacitor is taking out the stored charge on the capacitor plate. In order to discharge a capacitor, we connect the charge capacitor across a resistor. Now this is the same thing I showed you, and the resistor I used was a bulb. So when a charged capacitor is connected across a bulb, the charges flow through the bulb, lighting up the bulb. And what happened to the current with time? You can see the current decreases, is that right? With time. And gradually everything got finished. So the amount of charge, the rate of flow will be great in the beginning, and it will soon become very small. Well, when the switch is closed, in this case, the capacitor, the charges in the capacitor flows through the resistor, causing a current to flow in the circuit. Now, how does the current and voltage on the resistor change with time? The charge on the capacitor decays according to the equation Q equal to Q0 e to the power negative t over tau. You see, this is the equation for the charge when the discharge occurs. Now, if you look at this equation, I know you are familiar with this equation. What is the amount of charge on the capacitor plate when the time is 0? When time is 0, this will be e to the power of negative t over tau will be 1. Therefore, Q equal to Q0 in the beginning. So the moment you connect it at t equal to 0, the amount of charge equal to Q0. What happens as time goes on? When t is a large value, this quantity will be 0. That means after a very long time, the amount of charge will become 0. So the amount of charge will decay exponentially. And the voltage also decreases of the same form. V equal to V0 e to the power of negative t over tau. As the amount of charge increases, the voltage also increases. The current and voltage both approach 0 with time. So voltage decreases, the current also decreases, both approach 0 with time. So you must now be able to talk about the process of charging a capacitor and discharging a capacitor. All right. Now here is a good animation of charging and discharging a capacitor. This is a simpler circuit. A capacitor connected to a cell, and when the switch is closed as shown now, the battery is excluded. So this will be discharging. When I move this over there, the battery will get connected and the capacitor plates will start charging. So watch how the process of charging and discharging happens. I'm going to charge the capacitor now. You can see what happened. The charges moved from the cell and the capacitor plates now got charged. The charges on the capacitor plates are maximum. You saw the charges moving. How the amount of charge changed. With time, the amount of charge increased, and now this is the maximum amount of charge. What happens when you discharge the capacitor? Well, the charges flows and the charges are removed from the capacitor. So watch once again, charging the capacitor, discharging the capacitor. Alright, that's a very simple animation. I want you to watch one more time how the current and voltage changes in a capacitor resistance circuit while charging and while discharging. Now, here is how the current changes while the capacitor is charging. You can see the current from a maximum value decreases to 0. Watch that animation one more time. Current versus time when the capacitor is charging. Alright. Now, what will be while the capacitor is discharging? Remember, when the capacitor is discharging, the current goes in the opposite direction. So it will be negative maximum. It will come from a negative maximum towards 0 while discharging. Now watch how the current changes with time while the capacitor is discharging. While the capacitor is discharging, the current goes in the opposite direction. So while charging, the current reduced this way. While discharging, it reduces to 0 in the opposite directions. Now watch both that at the same time. Now current while charging, current while discharging. Alright, how about the voltage? Now the voltage, you can see this is the voltage while charging. The voltage grows, the current decreases. Well, I think you are now saturated with information, so let's get out of it. Let's now solve a problem. A 12-volt battery of negligible internal resistance is used to charge a 12 microfarad capacitor through a 200 ohm resistor. Find the initial current I0, the final charge on the capacitor, the time required for the charge to reach 75% of its peak value. Well, if you remember some of the equations we developed, this is a very simple problem. What do we know? Now, here is the circuit. We have a 12-volt battery connected through a 200 ohm capacitor, a 200 ohm resistor to a 12 microfarad capacitor. I0, well, the maximum current I0 equal to E over R. What is the EMF of the cell? 12 volts. What is the value of R? R is 200 ohm. That will be 12 volt over 200 ohm, and that is 0.06 ampere. You see how simple the problems are once you know the formula. B, what's B? The final charge on the capacitor. Well, QF equal to CE. Final charge is the maximum amount of charge on the capacitor. That will be C is 12 microfarad, E, the EMF is 12 volt. That is 144 microcoulomb. Well, C, the time required for the charge to reach 75% of its peak value. Well, we need to find T when Q equal to 0.75 of QF. You see, the amount of charge reaches 75% of its peak value. Now, can you recall the equation for Q, how Q changes with time? There is the equation. Q equal to QF times 1 minus e to the power t over tau. What is tau? What is tau? The time constant is R times C. So, this Q has to be 0.75 of QF. So, we need to find this time when this Q equal to 75% of QF. So we now replace Q by 75% of QF and then solve for T. Well, if you know how to solve a small exponential equation, then you are home with this. Now, that is, you can see QF will cancel from both sides. Is that right? QF will cancel from both sides. It means 1 minus e to the power of negative t over tau equal to 0.75, or e to the power of negative t over tau is 1 minus 0.75, that is 0.25. Alright, therefore, you see, if you now take the reciprocal, if e to the power of negative t over tau equal to 0.25, then e to the power of positive t over tau will be 1 over 0.25. Is that right? Reciprocal equal to 4. And therefore, what is t over tau equal to? if you take ln of both sides, you can see t over tau will be equal to ln of 4, isn't it? I hope you know this. Ln of e to the power of t to the power, ln e to the power of t over tau will be t over tau. So take ln of both sides. You get t over tau equal to ln 4, and using tau equal to rc, we have t over rc equal to ln 4, and since you know r and c, we can find that t. So t equal to rc times ln 4. R is 200 ohm, c is 12 microfarad, and that will be 0.0033 seconds. You see, if you use a very small resistance like 200 ohm, the capacitor gets its full charge within a very short time. Now, that has been a good part C, and I hope we will practice some of that kind of problems. Another problem. A 6 microfarad capacitor is charged to 12 volt and then connected across a 100 ohm resistor. Find A, the initial charge on the capacitor, the initial current through the resistor, the time constant, the charge on the capacitor after 3 milliseconds. It's not different from the one we did earlier. Alright, this is the capacitor circuit. I think it has probably gone off the screen for you, but it doesn't matter. The capacitor is 6 microfarad. The voltage across the capacitor is 12 volts. So the capacitor is charged to 12 volt. Now this is a problem of discharging the capacitor. Now, what is the initial charge on the capacitor? The initial charge on the capacitor is the maximum amount of charge. Q0 equal to CE, where C is 6 microfarad and E equal to 12 volt. That is 72 microcoulomb is the maximum amount of charge that is on the capacitor plates. B, the initial current through the resistor. Well, the initial current will be the maximum amount of current. I0 equal to E over R, and that will be 12 volts divided by 100 ohm, and that is 0.12 ampere is the initial current. What is the time constant? What is the time constant? Time constant tau equal to R times C. And R is given, C is given, so we have a 100 ohm times 6 microfarad, that is 600 microsecond is the time constant. And finally, D, the charge on the capacitor after 3 milliseconds. Now, what is the equation for the charge? How does the charge change with time? Q equal to QF times e to the power negative t over tau. Is that right? Yes. Q equal to Q0, that is the charge to begin with. That is this 72 microfarad. E to the power negative t over tau. Now, we need to find the amount of charge Q after 3 milliseconds. When this t equal to 3 milliseconds, what is the value of Q? We know all the values on the right side. Q0 is 72 microcoulomb, t is 3 milliseconds, tau we calculated is 0.6 milliseconds. Alright, and that will be 72 times 10 to the negative 6, is that right? 72 microcoulomb. E to the power negative 3 milliseconds divided by 0.6 milliseconds. We can leave both in milliseconds because it's a ratio of the same quantities. And that will be 4.85 times 10 to the negative 7 coulomb. After 3 milliseconds, this is the amount of charge left in there. We can write it in terms using microcoulomb. That will be about 0.5 microcoulomb approximately. Okay.